So I'm Paul, and this is Jim. My claim to fame this year is I named this presentation, so I get to take credit for that. Isn't that cool? Squeezing compression into SPDK. Isn't that awesome? Okay, so first, this is probably I think I know the answer, but show of hands, who's pretty familiar with SPDK, at least knows what it is? Okay, great. I mean, we're here every year doing 3 or 4 talks. I don't know, I think we have 4 talks this year between the Intel folks. So yeah, I won't spend a lot of time going over what SPDK is, but this is really to talk about the compression piece that Jim and I worked on this year. There's still some to-do items. We'll talk about that as we go. But this is really more about that. I'll give you enough context that if you're not familiar with SPDK, you'll know kind of what we're talking about. Okay, so we'll go over like super high-level architecture, and SPDK is so big, and there's so many different components. There's really no way that we could get through all of them and focus on compression. So I've really trimmed that slide down to just cover what we're talking about today. Talk a little bit about DPDK. You guys have all heard of DPDK, right? The other DK, PDK. I'm going to bring up the crypto BDev module. I actually was here last year with Fiona from the DPDK team, and we talked about the crypto module. That was our first purview into the DPDK framework. So I'll explain a little bit about how that works, give you the high-level flow of that, only because I think it's really interesting to see how that compares and contrasts with the compression, because the compression work was quite a bit more complicated than the crypto work, but they both tie into DPDK in the same way. Then I'll talk about the compression BDev module, or virtual BDev module, and sort of explain how that works. And then Jim will cover libreduce, or the reduce library. And as we go through the slides, you'll get a feeling for what that is and how that fits into the big picture. Okay, so here's the super high-level architecture. Like I said, it's missing a tremendous amount of components, but at the top is typically where we put our front-end stuff. So this is the example that I'm using here is the NVM over Fabrics target, which today supports both RDMA and TCP. So this would be the higher end, and then we're using NVMe as an initiator. And then this is our block device layer with just a few examples shown in here. And this is kind of the user space storage stack is the best way to think about it, right? We've got block devices which actually have something physical backing them, and then virtual block device modules that you can stack on top of block device modules to add functionality and capability like crypto and compression, and we've got a logical volume manager. So there's all sorts of different things you can do by adding virtual block devices. So what I'm showing here is just we've got all sorts of different virtual block devices, the DPDK encryption virtual block device, the compression block device, and then reduce lib, which is new with compression, which you'll see here in a minute uses persistent memory, and we do so through the persistent memory development kit, the PMDK. Then down at the bottom, NVM Express, we've got an environment abstraction layer in SPDK so that we can actually plug into any kind of environment like DPDK that supports the services that we use from DPDK, memory management, PCI management, all that kind of good stuff. Okay, next slide. All right, so DPDK's got a lot more than this too, but this is the slide we used last year to talk about crypto. You can see here's the crypto stuff over here. So they've got a crypto dev module and a compressed dev module that we're both using now. Now we chose DPDK Framework to implement these things because it's really cool for doing this, right? So if you guys are familiar with ISA-L, everybody knows what ISA-L is, right? That's actually out of our team as well, the team that Jim and I work on. So ISA-L does these things too. So we've been asked a few times, right? Why don't you just use ISA-L? Why are we using DPDK Framework? You can just bolt it right into SPDK, and we do use it for some things within SPDK. But the cool thing about, like take for example the crypto BBDev, they're actually both very similar. The DPDK guys have built a generic abstract API to hide whatever's behind it actually doing the crypto or the compression. So we write to a single API regardless of whether the backend is a hardware-assisted device or a software pulled node driver, which one of them happens to be ISA-L, or anything. So we really write to a generic API, and then anybody can go in and plug in anything they want in the end with very, very little integration work. And it's the same thing with compressed dev, right? So they followed the same model. There's one API for compressed dev, and then you can use a hardware assist on the back end, or you can use software Okay. Okay, so this is an animation, so I'll just sort of flip at you when I'm ready to go. Okay, so here's our, not yet, here's our SPDK application up here. And then I'm showing the block device layer. And this is the crypto example. Like I said, I wanted to go over this because it's a pretty simplified view of the world. And then the BDEV is actually the block device that's representing the device. So this would be an NVMe BDEV in the example I'm talking about. And then this is our virtual BDEV that we just stack on top of it. So you could actually put crypto on top of anything. You could put it on top of a logical volume. You could put it on top of an NVMe BDEV. You could put it on top of a RAM disk. You could put it on top of anything you want. And then we've got our SSD down here, of course. And then off to the right, this is where we've got DPDK. This is the CryptoDev API. So this is the generic API I was talking about. And then the two examples are ASNI pulled mode driver and the QAT pulled mode driver. So that first one is a completely software-based cryptography. And the second one is the Intel Quick Assist card. And from our perspective, writing this module, it's basically the same API, right? Both asynchronous, fire them off, pull them, and get the completions. Okay, so let's start with the first click here. So an I/O comes down from the application, and its first stop is the crypto virtual BDEV module, because that's how this thing was configured. Its next stop is going to be the crypto is going to take that I/O, whether it's a read or a write, and it's going to fire it off asynchronously over to the CryptoDev framework. And we've got a poller that's going to be running over here and cruising along looking for completions on those. And as soon as the operation is done, the crypto or unencryption is done, then it comes back to the crypto BDEV driver with the buffers identified and what's in them. So then what we do is we take either the encrypted data or the unencrypted data, and we fire it down to the BDEV, which the BDEV in turn fires it down through the driver and gets it out to the SSD. So pretty simple example, right? And I mean, that's the beauty of the virtual block device model that we've got. It allows us to do these kind of things pretty easily. Okay, so let's talk about the big picture here for compression. You can see there's a couple of new things on the slide. The first, most prominent one is like persistent memory. So we use persistent memory, and we can get into a lot more detail of this when Jim goes through the libreduce. But in order to efficiently allocate and keep blocks stacked up as we compress the data, it requires a lot of metadata operations, right? So we have a need for very fast metadata operations. So it's basically a really good fit for persistent memory. The other stuff in here that's new that you see on top of the compression driver is libreduce and PMDK. Okay, so libreduce is its own module. It's only used by the compression virtual block device. But this model is a little bit different than what we saw before. And as I walk you through this, it'll become clearer. The compression VBDEV in this implementation is much more of a traffic cop than it is a virtual block device in the sense of what we just saw over there. When it comes up and initializes, we trade function pointers back and forth with libreduce so that libreduce knows how to talk to raw disks. It knows how to do a compression and decompression operation, but it does so all of them through the compression virtual block device module. Okay, so let's click on the first one here. First thing that happens is same as with crypto, it still comes down to the compression driver. So the compression driver gets a read or write operation to a logical device of some kind. And instead of firing over to the compression framework like we did in crypto, now what we're going to do, go ahead and click Jim. Now what we're going to do is we're going to take that read or write and we're going to tell libreduce, hey, there's a read or write, but I don't know anything about the physical layout of the disk. I don't know whether the data is compressed or not. I don't know anything about it. So it fires that off to libreduce, and libreduce is going to do some metadata operations through PMDK, so it's talking to its persistent memory. And then it gets a little bit complicated, so the slide isn't completely accurate for what the code does. But then libreduce, go ahead, Jim. Libreduce is going to call back into the compression VBDEV module with some function pointers that we trade at initialization time and say, okay, here's the data that you need to compress or decompress. And then the compression VBDEV module does the compression operation and actually gets back to libreduce and says, okay, now this is done. And then we take the completed operation and fire it down to the BDEV, and it makes it out to the SSD. So, like I said, a little bit more complicated than crypto, but pretty cool that we've got good use of persistent memory. and use of PMDK. I'm sure you guys have seen all the PMDK stuff going on this week and over the last couple of years. Really easy bolt-in, really convenient to use for us. Okay, so with that, I'm going to turn it over to Jim, who's going to go through the details of libreduce and how we actually take advantage of the compression algorithms that DPDK gives us.
Okay, can you guys hear me? Okay, so Paul gave a really good overview of how this libreduce library fits into the overall SPDK picture. So I'm going to focus now mostly just on that compression library itself. We purposely wanted to build this library so that it wasn't tied exactly to the BDEV interfaces that Paul talked about, so that it could be used standalone. It really helped us kind of make sure that the APIs were correct. It made it really easy for us to build test infrastructure around it. And it means that you could pick up this library and you could use it in a different context. It's not tied directly to our SPDK block device layer. So go ahead to the next. So there's... Oh.
You go back right there.
There we go. Yeah, so go ahead to the next. So there's three main pieces to this library. So the first one to construct this is you need some sort of block device for your backing I/O units. I'm going to use this term backing I/O units here. It's basically the where we're going to store the compressed blocks on disk. I'm going to talk about some cases where we actually don't store compressed blocks. We store the uncompressed blocks, and so this backing I/O, these backing I/O units and the backing I/O device really refer to that. And so with this implementation, we're going to typically be using a thin provisioned SPDK logical volume, so that as we start writing blocks to that logical volume, that'll actually start consuming the capacity, and that's how we're going to realize our savings. So the key one here is that we're using a persistent memory file for the mapping metadata. So if you've done block compression, you know that you have this problem where you've got maybe 16K of data that's coming in and only 8K of data that's coming out, and you've got to keep track of how those uncompressed blocks map to the compressed blocks on disk. And so we really thought using persistent memory would be a really unique way to take advantage of that byte persistence. And so we're using PMDK directly to read and write that persistent memory file. Let me go ahead and hit the next one. We do have some amount of metadata on the block device. So for example, in the SPDK block device, when block devices start showing up in the system, so for example, let's say a logical volume is exposed, we need to know if this logical volume, does it have a compressed, I mean, is it compressed? And so we store a small amount of metadata at the beginning of the block device with some parameters describing how we're using libreduce. So for example, things like the path to the persistent memory file, how big is the chunk, how big are the I/O units, some of those parameters. And then the key thing is this is a metadata algorithm only. We're not implementing our own compression algorithm. We're going to use standard compression algorithms like deflate, LZ4, et cetera. This is just describing the algorithm we use for the mapping this metadata and how we store it on persistent memory. Okay. So this is going to talk a little bit more about how this library fits into things like the SPDK block device layer. Go ahead and hit the first. So the first part here is we have, at the beginning when you want to create a what we call a reduce volume, you're going to call this reduce vol init, and it's basically going to call into here. You're going to pass it the block device, and you're going to pass it a path for the persistent memory file. It's going to go ahead and create the persistent memory file, store the metadata on disk, and return to you a handle that you can then use to start doing read and write operations. And then later, you can do a load operation. So we use this load operation whenever we get a new block device. This will tell us not only load a existing compressed volume, but you can also use it to say, is there a compressed volume on this block device? So we use this in the SPDK path whenever we identify, we have a process called examine. Whenever a new block device comes up, each of the virtual block device modules get a chance to see, do I want to claim this block device? And this is what we use for that. This is how we can tell whether any existing block device is a compressed volume or not. Then these are the read V and write V is how the upper layer application actually performs read or write to do read or write operations to the compressed volume. And then on the bottom end, this is where we end up with a number of operations. So one is, if you know anything about PMDK, if you don't, definitely attend some of the persistent memory sessions. I know Andy Rudolph's going to be doing a hackathon with PMDK, and you can understand more how this works. Reading and writing to persistent memory is just load and stores. There's no special API there. But we do need at very critical junctions when we're updating the metadata to actually make sure that it's persisted. And so we'll make calls out to PMDK to persist the specific regions. Go ahead and hit the next. We'll do read V, write V, unmap out to the backing I/O device. So whenever we have to go and read compressed blocks or write compressed blocks or unmap blocks, we'll make those calls. And then go ahead and hit the next one. And then, of course, there'll be cases where we'll have to go and say, we want somebody to go compress, decompress some data for us. So we don't, inside of here, we're depending on something outside of us, in this case, Paul's compress BDEV module to actually do that compress or decompress operation. This is not tied specifically to the DPDK framework. The DPDK framework stuff is handled in the module that Paul talked about. So to kind of summarize here, this is completely independent from the SPDK framework and the BDEV layer, so it can be used as a standalone module. I'll talk a little bit about what chunks mean. So whenever you're doing compression, you have to decide, what chunk of data are you going to compress on. We decided for simplicity to force the caller. If we say that a chunk is 16K, and you have an I/O that spans a 16K boundary, it's up to the caller to actually make sure that those I/Os are split. We already have quite a bit of functionality in SPDK and other areas of the code to do this splitting, and so we decided to leverage that and not duplicate all that here in the libreduce library. And then it's single-threaded. So for each compression volume, there's operations where you have to make sure that you synchronize. If you've got multiple writes going to one chunk, you have to synchronize them. Within SPDK, we can pass messages between threads very, very quickly. And so from a complexity standpoint, we decided to make this single-threaded, and then we have code in the upper layers that make sure that if you have multiple threads that are sharing the same volume, they will send them to one thread to make sure that those I/Os are all synchronized. Okay, so layout. So I'm going to describe a little bit about how the data is actually laid out on the SSD and in persistent memory, and then I'm going to go through a few examples on what read and write operations actually look like. So first we've got the SSD. Go ahead and hit the next one there, Paul. So we split this up into the I/O units. So for this example, we're going to assume each of these I/O units is 4K, which means we're always going to be reading or writing to the backing I/O device in 4K units. And next we have the persistent memory file. And this is, the persistent memory file is split up into two main pieces. The first one is a chunk map. So a chunk map contains what we call chunk entries. Go ahead and hit the next. So what this does is, you can think of each of these chunk entries as representing 16K of data. So in this case, what we're saying is that we have 16K of data. It was able to be compressed down to 10,121 bytes, which means that it would take 3 4K units to store that data, and then it points to those 3 units. And then finally, we have the logical map, and then this basically points to the user visible logical map. When they say, I want to write to LBA 0, well, that means we're talking about this here. If they're talking about LBA that's at a 16K offset, that's going to be this entry. And so this is where we basically store an entry here, which points to the chunk map entry. And that's kind of how all these pieces fit together. OK, so let's walk through a couple of examples. OK, so the first one, we've just initialized the logical volume. So we have no data on this whatsoever yet. User says they want to write 4K of data at LBA 0. So first thing we do is we look up in the logical map, this is empty. So we know this is, there's no existing data. We don't have to worry about any kind of read, modify, write operation. So the first thing we do is we keep a bitmap in memory of the chunk maps and which ones are used and which ones are allocated. So first we're going to allocate an empty chunk map, entry 0. Then we're going to compress the data. So I'm going to call out to Paul's module. I'm going to say, I want you to compress this 4K of data with 12K of zeros, because we're only writing 4K out of the 16K chunk. And let's assume this compresses down to 2,500 bytes. So since it compresses down to 2,500 bytes, it means we just need one I/O unit, one 4K I/O unit. So we're going to allocate one of those. So then here we write that compressed block to disk. We go ahead and we write the chunk map entry. And then this is the part that makes it what I would say is official. That's when it's basically committed. Once we write to the persistent memory, the logical map, then the next time somebody goes and reads the data, they're going to find that data and they're going to be able to read it. So you can see kind of how these point to each other here. Let's go ahead to the next. Okay, so now we'll do, now we're going to write a full chunk. We're going to write a full 16K to offset 64K. Go ahead and hit the next. So here we can see this is empty, right? So we, it says 16K. This should have said 64K. So we're going to look up here. This is empty. There's nothing there yet. We're going to allocate another chunk entry in the map. Okay, so now let's say we compress this 16K and it only compresses to 14,000 bytes. So 14,000 bytes, it's going to take 4 I/O units to be able to store that data. So why compress it, right? If we compress it, we might as well just store the uncompressed data on the disk so that then later we can just read it back and we can save time. So we'll actually allocate the 4 backing I/O units, but we're going to write the uncompressed data to the disk instead. And go ahead and hit the, and then again, we're going to store this here. Since we see 16384, then that's going to be our clue later that that's uncompressed data. So we'll know that when we read the data back, we won't have to decompress it. And then again, we write and persist the logical map entry. Okay. So now we're going to write to offset 4K to this chunk that we already wrote to earlier. And this is going to be a really good example of showing why persistent memory works really well here, why the byte, being able to do byte addressability and 8-byte atomic operations makes this a really nice solution. So we look up the entry, we find something. So now we know we can't just take our 4K of data and write it. We've got to read the old data, we've got to merge it, and we've got to write new data back. So we're going to read the I/O unit. We're going to decompress it into our data buffer, and then we need to merge the incoming 4K. So we got the old data that was out on disk. It was that original 4K that the user had with a bunch of zeros, and now we're going to merge this 4K of incoming data into that. Go ahead to the next. So here we're going to say this compresses down to 5,000 bytes. So now this means we need 2 backing I/O units. So one of the things I want to call out here is that we never update anything in place, right? So you can see here, we don't overwrite this chunk map entry. We're going to allocate a new one. And same thing here for the backing I/O units. We're not going to try to reuse that entry 0. We're going to allocate two new ones. And when the volume gets initialized, we account for this. We account for extra space in the persistent memory file. We account for some extra space on the SSD, so that we can make sure that we have extra space. We don't have to do any of these in place. So now we've written the compressed data to the SSD. We write and persist the chunk map entry. And then this is the really, actually just go back just one. So you can see here, as of this point, this still is not committed, right? If the system were to crash at this point and we came back up, this is still going to point to the old data. So now when we do so at this point, we persist this first, and then we write this. And only once this is written is the data actually committed. And so this is how we can really make sure that the persistent memory allows us to atomically be able to update these chunks so that it's going to be power fail safe. So this is probably a good point to call out that when we reload, so here in memory, we can release the old chunk entry in the I/O units. This is only releasing it in our internal in-memory bitmaps. We don't have to write anything to disk to actually free them. When we load this thing back up later, we're going to walk through this list, and this is going to tell us which of these entries are valid, and these are going to tell us which of the I/O units are used, and that's going to implicitly free everything that may have still been there from when we ran previously. Okay, trim is pretty easy, especially if you're doing, trimming a full chunk. Go ahead and hit the next. Basically, all we have to do is we just clear this. So we can just go ahead and hit the next one. So we clear that out. That implicitly releases those chunks because now when we come back up, when we read that, there's not going to be anything there. So there's nothing referencing this chunk map entry. There's nothing referencing those 4 units on disk. Okay, and then the final example here is reading some of the data back. Sometimes after you write the data, you want to read it back. So we're going to look up the chunk map entry. Go ahead and hit the next one here. So here we're going to read those 2 backing I/O units, 5 and 6. So what we can do here is, since the user's only reading 4K, we can actually target the user buffer for the 4K that he's interested in and just use a bit bucket for the other 12K. Because we want to try to avoid having to read the data into one buffer and then copying it over into the user buffer. Okay, so that was a whole bunch of examples. Hopefully that all made sense. We do have some next steps here. One of them is on the unmapped path, we have some optimizations we can make for doing what we're calling sub-chunk allocation masks. So right now, we're not keeping track in the metadata of like which LBAs in the chunk have actually been written to. Some of those cases where we're like writing zeros, we could actually make some optimizations where we don't have to do that. We could save on some bandwidth. We're really hoping we would have some really cool performance charts for this. We don't have the charts yet. Once we do, they will be out on the SPDK website. Some of the initial data looks good, but there's still some things that we need to run through. We still have some additional on-disk metadata parameters that we want to store on disk that's not being stored yet. Go ahead and hit the next one. And then we have some methods for reducing the metadata file size. So right now, the chunk entries, when they refer to the I/O units, they're using 64-bit values for those. And we've got some methods where we could do 32-bit instead. So we would still support volumes that have more than 2 to the 32 I/O units. But with a little bit of extra finagling, we can effectively cut the size of the metadata file in half. And that's when you start looking at cost effectiveness of this. That's one of the things you want to do, right? Because the persistent memory is more expensive than NAND, of course, and so we want to make sure we're making use of that persistent memory as well as we can. And I think that is it. If you want to get more information, there's tons of info out on our SPDK.io website. A lot of information on the documentation link that goes through a lot more details on what Paul talked about, and there's some more details on LibReduce here as well. One thing to call out, we're actually having a developer meetup here in the Bay Area. What is it, November 11th and 12th. So if you're interested, if you're somebody who is hands-on and wants to engage in a really deep dive technical session over about a day and a half, check this out. There's an opportunity to RSVP for that.
Yeah, that one's actually hosted by Nutanix also.
Yeah. So with that, questions, Jay?
So with regards to the unallocated boxes, how do you handle sanitization?
You want to
sanitize the drive so that for security purposes. How do you handle the sanitization of the actual data on the drive at that point, since you've got so many redirections?
Yeah. So, I mean, typically, if you have some of that, let's say we take a logical volume, and then we're going to make that compressed. That is typically going to go to one client, and then so I think your question is what happens when that storage is going to be repurposed for some other client. So in LibReduce, we're not handling that sanitization part there. That would be handled at the layer where you allocate the logical volume. So with that logical volume, you have the opportunity to sanitize that logical volume before you repurpose it to create storage for some other client.
So in the model that you had before with the three stages, you've got the chunk data, you've got the logical data, and you've got the actual write to the
Yeah.
drive. So LibReduce isn't handling all of that. You're still relying heavily on some of the physical media for some of this. Is that right?
Yeah. So LibReduce is handling these parts here, but everything here is associated with one compressed volume.
Okay.
So.
But the virtual volume.
Yes. Yeah. So typically what happens is how about I take a step back and walk through the process of how you get one of these set up. So the first thing you would do is, let's say you want to create a 10 gigabyte compressed volume. So the first thing you're going to do is you're going to create a 10 gigabyte logical volume on the SSD. Then you're going to take that 10 gigabyte logical volume and you're going to pass it to the LibReduce. He's going to create a compressed volume that's going to be 10 gigabyte minus a little bit for some of those extra blocks we talk about, so we don't have to do things in place. But then that 10 gigabyte is going to be assigned to one client, maybe an NVMe over Fabrics client or a VM, et cetera. And then LibReduce is going to handle this. It's also going to handle the persistent memory. At some point, once that logical volume is no longer needed, you're going to destroy the compressed volume, which is basically going to zero the portion of the logical volume. And then it's also going to delete the logical volume because this is no longer needed. Right. So
I was going to say, just in case it's not clear, logical volume and compressed volume are two totally different things, right? So logical volume is a different abstraction layer, and maybe it helps if you think about it. The very top layer that's exposed to the application is the compressed volume. The compressed volume and all this stuff sits on top of a logical volume, which abstracts away what's underneath it. Right. So we've got multiple layers of abstraction here. So that's why you're saying when you delete the logical volume, independent of the compression volume, you've got the option of saying, destroy this when I start it or destroy this when I complete it and wipe out all the data.
The genesis of the question
Yeah.
is if I've got a host that's going to be sending a sanitization command to the drive, right, and I'm going through this method of where the logical volume is being managed by SPDK,
Right.
where does...
Oh, you're talking about sanitized operations that are coming from the top end to the compressed volume.
Jay, don't call them sanitized. Sanitized applies to an entire device, a physical device. You're talking about secure data deletion, which might be of a namespace or something.
Fair point.
You're confusing everybody by using that word.
My apologies.
At least me.
Bad Jay.
Hey, if you're confused now, just hang around for a couple hours.
Yeah, so right now, I mean, we have unmap operations support on the top end. Looking at sanitize is something we probably need to look at. That's a good.
Yeah, we'll either do unmaps or write zeros in the operation we're talking
Yeah.
about.
Yeah, please.
Your thoughts on putting this, chunks mapping and all the metadata directly inside SSD and making use of, so SSD already has lots of internal maps, FTL and all those stuff like that. This is a very similar thing which, this mapping is required.
Mm-hmm.
So what about taking this and putting it in the drive itself?
Yeah, so your question is like this stuff, put it in instead of persistent memory. So PMDK actually supports that. PMDK, you can actually have a file that's on disk, and what it'll do is it'll mmap this, and then when you do the pmem persist, it's actually going to do an msync. So you can actually do this on disk today. It's just going to be slower because when you want to update 8 bytes, you're updating a whole block.
Quite a bit slower. Yeah.
What's that?
Quite a bit slower.
It is going to be quite a bit slower. So there certainly are ways that you could put this on disk that might be faster. This was one that we purposely implemented to take advantage of persistent memory. If you wanted to have one where all of this metadata was stored on disk, this may or may not be the best algorithm to do that, but this one is well tuned if you do have persistent memory on your system. Go ahead.
Can you do compression and encryption in the stream one into the other and only then off to this whole device?
Yes. Yep.
And the SPDK keeps those in the correct order? Meaning compress before encrypt?
Well, so you could decide to do encrypt before compress. I mean, if you decide to set it up that way, we don't, if that wouldn't be a smart way to do it, so we don't enforce it. We don't say like, well, that's a stupid way to layer them. But it does support, the user configures that, yep.
Yeah,
Yep.
the crypto and compression VBDEV modules are completely independent.
Yeah.
I see. Okay, but as far as streaming one into the
Yep.
other, so the encrypted stuff would be, the compressed data
Yep.
would just stay in RAM and then go into the encryption piece.
Yeah, so what would happen is if you, why don't you go back to my intro slide. Sorry, there's lots of animation.
The thing is just you don't have to actually go all the way to the device.
Yeah, so here, so go forward here. So here, if you had an encrypted block device down here, then this is basically going down to that device instead. And then that in turn could go to the logical volume manager, and that in turn could go down to the actual SSD. So these can really stack on top of each other.
I have one other question. What if you want to demount the compressed volume? Will you then take the metadata file, push it out there, and be done so you can reuse your non-volatile memory for whatever is coming up next? Assume that there is mounted all the time, therefore you have to keep the metadata in all the time.
So if you want, let me make sure I understand what you're asking.
Well, is it meaningful to unmount the compressed volume because the user who's using it
Yeah.
isn't using it anymore, but later at some point they will, and so you would remount it at that point, continue operation?
Yeah, you can certainly do that. I mean, you have to keep the persistent memory file on disk. We persist the path to that file. So you could, you could unload all those. You could unmount the persistent memory file system. But if you wanted to come back and you wanted to load that volume again, you've got to make sure that the persistent memory file system is loaded so that it can find that file.
Okay, and that file, then that's all handled through libreuse.
That's right.
Okay.
Yep. In the back?
I've written this in years past, so I have a few questions.
Okay.
So I understand the limitation. It looks like you're throwing away 12.5% compression ratio because of your allocation.
There is some, yep. Yeah, there's some cases where we're doing some rounding and there's some bytes that are,
Well,
yep,
it's 4K, so that's a pretty big graph.
yep,
When I've done this in the past, it's been at 16 and 64 byte pieces.
yeah.
You don't look like you have any way to prevent your target blocks from being fragmented.
Can you clarify?
Well, the target blocks, as you use the volume for a long period of time,
Yeah.
will eventually end up with single blocks that are scattered throughout the
Yeah.
volume that are no longer linear.
Yeah.
Is that true, or have you done any analysis?
No, so that's certainly true. I mean, that's kind of how the SSD handles it internally anyways. Right, like if you go back to, let me just, let's go to here. Yeah, so I think what you're saying here is now you have a case where you've just got one block here in isolation.
Eventually, you'll have holes all over the place.
Yep, yep,
Start
yeah,
using them less than 4K at a time, 4 at a time.
yep.
Okay. So you don't have any type of garbage collection to try to recover that linearity.
Yeah, so we felt like since the SSD is already internally doing FTLs on a 4K granularity, as you're writing to the SSD, it has its own log typically in the SSD, and so even though the LBA numbers themselves may not be contiguous, that data still ends up getting written contiguously on the SSD. So we felt like the having a bitmap here where we can just pick the next 4 open blocks would be sufficient for this algorithm.
As you consider, to go back to the first question, which I understand is old data is still very visible to anyone who has access to the underlying device. That's how I view his first question. Have you considered adding a coordinated support between the compression and the encryption layer so that the encryption actually changes with every compression generation, so that you can no longer get to old data meaningfully?
That's an interesting idea. We haven't talked about that in terms of this. I mean, for what we've talked about today, they're two distinct layers. They don't really have knowledge of each other. Something like that could certainly be done, but that's.
You understand what I'm saying?
Okay.
Conceptually, that would alleviate the problem of stale data still being reachable.
Yeah, but
Using a different crypto key for every block.
yes, I think you would just have to keep track of what are those keys that you have for each block, right? So that you could read it back later. Yeah.
And going back to this gentleman, have you considered creating a region on the block volume that is the same size as your persistent file, so that you can copy the persistent file to the volume?
Yeah,
That gives you a portability.
well, no, I mean, that's a really good, so we have heard that. We haven't implemented that yet, but that's something that I think we'll probably do, because that does make it easier to be able to, maybe move it from one system to another. And of course, that metadata file on disk isn't going to be updated every time you do an I/O, but it would be a way to be able to, if you had an operation offline, then it would make it easier to be able to move that logical volume between systems.
When I did this years ago,
Yeah.
I didn't have any persistent memory, so I had to update
Yeah.
with
Sure.
blocks.
Yeah.
So it was more of a linear stream.
Yeah.
And
Yep.
as a linear stream is blocks,
Yeah.
it's going to become a bandwidth problem,
Yeah.
and not an IO problem. I think your allocation units create an interesting write-amp and an interesting loss of compression problem, but I think.
Yeah, there's always a trade-off. I mean, with any algorithm, there's definitely a trade-off on speed versus compression ratio, and so this is.
You have garbage collection. You
Yeah.
just go down to bytes.
Yeah.
Not saying that that's the right
Yeah.
solution, but you have to have garbage collection to be able to do that.
Yeah.
Now you're ready.
Okay. Yeah. Let me. I think there was another.
It was a similar question.
Yeah.
Similar question. So what about reusing the blocks, the I/O units? So you said that you don't have garbage collection.
So we do have garbage collection. So in this case here, here's a case where we did a read, modify, write. We no longer are using this block. We don't have any logical map entries that are pointing to this. So we will clear the bit in memory so that we can use this again. And if the system reboots, it will see that there's nothing referencing this, and so this bit will stay clear as well, and we'll use it the next time we boot. So we are doing garbage collection in memory. We're not doing garbage collection from the standpoint of trying to get contiguous LBA regions.
Could be fragmentation in that.
Yeah, there could be fragmentation. Yeah. I mean, the one advantage, which is something we would need to explore, is that if you have 3 blocks here and 1 block here, that's 2 write operations. You can't do that in one, because when you do a write operation, you can only give just an LBA range. Whether or not that makes it faster, that's up for, we'd have to take a look at that, but that'll be for next year's talk. Any more questions? Yes.
I suppose that the compression is done in the initiator, yes?
I'm sorry, the compression's.
Done in the initiator. If you have the payment device, which is a node,
I mean, you could do the compression on either side. You could do it on the initiator or the target side. It would really depend on, I guess, your use case.
If your file is a shared file between different users?
If your file is a shared file between different users. I think even if you had a block device that was shared between multiple clients, on the target side, you could still have the compression done on the client side. And then as clients were connecting to it, I mean, they're each going to decompress the data. But it's going to be on the target side before the data is returned.
Yes, but you have the merging process. If your device is remote,
Mm-hmm.
performance issues.
You mean because you're transferring the uncompressed data over the network instead of the compressed data? Yeah, so I think that would come down to if it's a shared volume read-only, then certainly doing the decompression on the client side would make more sense. If it's a shared volume, but I mean, typically you're not going to have shared volumes where they're both writing to it, because that just wouldn't work, because then you would have no way for those clients to coordinate the metadata updates. But I think it would just kind of depend on your usage model on which side you would do it on. I think there's cases both for the initiator side, like you're talking about for the shared volume, but I think there's a lot of cases where doing the compression on the target side makes sense as well. A lot of times clients may not always have, the offload engines or things to do the compression most efficiently. And a lot of times those might be built into the target, and the target can do that compression or decompression very efficiently.
Yes, it's a conceptual feature.
Yeah.
Compression.
Yep.
If you detach your device from the initiator, how can you restore the data? Where is the persistent memory supply?
Yeah, you have to keep the persistent memory with.
Which is the device.
Yep. Yep. And so certainly if it's on the target side, that's easy to keep those together. On the initiator side, at least for this mechanism, you would have to have the persistent memory file be able to be accessed by other clients as well. So, yeah, there's some trade-offs. Certainly, if you're doing this on the client side, yeah, sending that persistent memory file to all the clients may work, but it would be using that across, you'd be duplicating that persistent memory file across all the clients. So, any more questions? Okay. Well, thanks everybody. Lots of good questions. Appreciate the feedback.